Imagine waking up one morning to find that your personal information has been stolen. This is exactly what happened in the infamous Yahoo data breach of 2013. The year was 2013. The internet was buzzing and Yahoo reigned supreme as one of the biggest giants in the world of digital communication. However, beneath this facade of success, a storm was brewing. Hackers had managed to infiltrate Yahoo's systems and compromise nearly 3 billion accounts. That's right, 3 billion, an incident that still holds the dubious distinction of being the largest data breach in history. You might be wondering, how did this happen? How did hackers manage to bypass a tech giant's security measures and gain access to such a vast amount of data? The answer lies in the lack of proper encryption. Yahoo failed to adequately encrypt its user data, essentially leaving the door wide open for hackers to stroll in and help themselves to a treasure trove of sensitive information. Now, this is where cryptography comes in. Cryptography, in its most basic form, is the art of writing and solving codes. It's like a secret language that only the sender and the receiver can understand. If Yahoo's data had been properly encrypted, it would have been jumbled up into an unreadable format for anyone without the correct decryption key. This isn't to say that cryptography is a silver bullet. It's not. But it's a shield. A strong one at that. It's a measure that can significantly raise the difficulty level for hackers, making it more trouble than it's worth to try and crack the code. In the digital age, where our lives are increasingly intertwined with the internet, the importance of cryptography cannot be overstated. It's our first line of defense against data breaches, identity theft, and cybercrime. If Yahoo had used stronger cryptography, it might have saved billions of users from data theft. But what exactly is cryptography? To understand it, we need to go back in time to the very origins of this science. Cryptography, in its most basic form, is the art of writing or solving codes. It's been around for thousands of years, even before the time of Julius Caesar. But let's go further back, to ancient Egypt around 1900 BC. The Egyptians used a form of cryptography known as hieroglyphs, a system of picture writing, to inscribe tomb walls and monuments. Fast forward to the Roman Empire, where Julius Caesar used what is now known as the Caesar cipher. This simple shifting cipher was used for communication during military campaigns, proving the importance of secure messages in warfare. In the Middle Ages, cryptography became more complex. The Arabs developed frequency analysis, a method to crack monoalphabetic substitution ciphers, shining a light on the need for more sophisticated techniques. In the 20th century, cryptography took a giant leap forward with machines like the German Enigma during World War II. This marked a shift from manual to mechanical encryption, changing the face of cryptography forever. Post-World War II, the digital age began, and with it came the need for more advanced cryptographic methods. In the 70s, public key cryptography was developed, allowing two parties to communicate securely over an insecure network. Today, we live in an era of quantum computing and blockchain technology, pushing the boundaries of cryptography further than ever before. Modern cryptography uses complex algorithms and mathematical theories to secure our data and communications. In this digital age, cryptography is not just about secret messages anymore. It's about data integrity, authentication, and non-repudiation. It's about securing our digital identity and our online transactions. It's about protecting ourselves and our information in this interconnected world. From hieroglyphs to digital signatures, cryptography has come a long way. And as our world becomes increasingly digital, the importance and complexity of cryptography will only continue to grow. We're just at the beginning of this journey, so buckle up, because the future of cryptography is going to be a wild ride. At its core, cryptography is all about transforming information. But how exactly does this transformation take place? Let's delve into the basics of encryption and decryption. Picture this. You have a secret message you want to send to your friend. You don't want anyone else to read it, so you decide to code it. This is encryption in a nutshell. The secret message is your plaintext. By applying a cipher, a set of rules for altering the message, you transform it into an unreadable ciphertext. But how does your friend decode this unreadable message back into the original? Here's where decryption comes into play. Your friend needs to know the exact cipher you used and apply it in reverse to convert the ciphertext back to plaintext. Now, You might be wondering, what if someone else knows the cipher? This is where keys come in. In modern cryptography, a cipher isn't enough. You also need a key, a piece of information that dictates the output of the cipher. When you encrypt your message, you use a key, and when your friend decrypts it, they use the same or a corresponding key. This ensures that even if someone knows the cipher, they can't decrypt the message without the key. And that brings us to algorithms. An algorithm in cryptography is like a master recipe. It details how to apply a cipher and a key to encrypt or decrypt a message. There are many different algorithms, each with their unique strengths and weaknesses, and they are constantly evolving to stay ahead of those trying to break them. So, to sum up, encryption is the process of transforming plain text into ciphertext using a cipher and a key, while decryption is the reverse process, turning ciphertext back into plain text. They are the fundamental processes that allow secure communication in a world full of prying eyes. Encryption and decryption are the heart and soul of cryptography. Now that we understand the basics, let's delve deeper into the world of cryptographic protocols and algorithms. Imagine trying to construct a building without tools. It would be impossible, wouldn't it? The same applies to cryptography. Without protocols and algorithms, it's just a concept. So, what exactly are these tools? First, let's talk about cryptographic protocols. These are procedures that ensure secure communication in the presence of adversaries. They are like the blueprint of a building, outlining how each part should come together to create a secure structure. Now, onto algorithms. Cryptographic algorithms, also known as ciphers, are the methods that transform plain text into ciphertext and vice versa. They are like the tools used to construct the building, each with a unique function. One of the most well-known cryptographic algorithms is RSA, named after its inventors Rivest, Shamir, and Adelman. RSA is a public key encryption algorithm used widely for secure data transmission. It's like a power drill, a versatile tool that can perform multiple tasks. Next, let's touch on DS, or Data Encryption Standard. DS is a symmetric key algorithm for the encryption of digital data. Although it's now considered to be old school, in its heyday, DS was like a reliable hammer, always getting the job done. In response to the vulnerabilities of DES, the Advanced Encryption Standard, or AES, was developed. AES is a symmetric key algorithm that is robust and efficient. Think of it as a modern, high-powered nail gun. It's faster and more secure than the old hammer. These protocols and algorithms work together to ensure the security and integrity of data. They are essential in our digital world, protecting everything from our personal information to national security data. Remember, cryptography is like constructing a secure building. You need a solid blueprint, the protocols, and the right tools, the algorithms, to ensure the structure is strong and secure. These protocols and algorithms are the tools that make cryptography work. So, where do we use cryptography in our everyday lives? Let's start with the most common application: secure communication. Ever sent a private message on WhatsApp or made a video call on Skype? Well, you've used cryptography. These platforms use end-to-end encryption, making sure that only you and the person you're communicating with can read or listen to what's being shared. No one else, not even the companies themselves, can decrypt and peek into your conversations. Next, digital signatures. They're like the electronic equivalent of your handwritten signature, but much more secure. When you digitally sign a document, you're using your private key to encrypt the document's hash value. This allows anyone with your public key to verify that the document was indeed signed by you and hasn't been tampered with. And how about when you're shopping online? Ever notice the padlock icon in your browser's address bar? That's Secure Sockets Layer, or SSL. At work, it's a cryptographic protocol that encrypts your credit card information and other sensitive data, ensuring it gets safely from your computer to the online store's server. Then there's cryptocurrency. You've probably heard of Bitcoin, the digital currency that relies heavily on cryptography. It uses cryptographic functions to secure transactions, control the creation of new coins, and prevent fraud. Finally, secure cloud storage. When you store your photos, documents, and other files in the cloud, they're often encrypted to protect them from unauthorized access. Some cloud services even offer zero-knowledge encryption, which means only you hold the decryption keys, not the service provider. In a world where data is the new gold, cryptography is the lock that keeps it safe. Whether you're chatting with friends, signing a digital contract, shopping online, trading cryptocurrency, or storing files in the cloud, cryptography is working behind the scenes to keep your data secure. So, the next time you use any of these services, remember, you're using cryptography too.